Recording is rolling. It's Thursday, November 9th, the end of the week, because we're going into 3-day weekend with Veterans Day. Veterans Day tomorrow. And so we're going to finish this momentum half page that we've been working on earlier this week. Then we'll start on your guys' textbook puzzles for, let's see, guys, it's chapter 9. So we're going to start on these later today. Oh, don't worry about AP stuff. That's you guys. All right. Oh, rocket launches. We got a bunch of rocket launches happening this weekend. There's one tonight, 8:28. So that's that. And then Saturday and Sunday, got a couple of rocket launches. While I'm doing announcements, we got an email from Mr. Dravies about Powder Puff. So if you're interested in Powder Puff, there's going to be a meeting next school days on Monday after school. Monday after school in the Media Center. So if you're interested in that, Monday after school in the Media Center with Mr. Dravies. All right. Let's hit this momentum half page. Okay. I think the last one we did was number 7, the elastic. Oh, yeah. Oh, no. All right. So last one we did was number 7. I didn't circle the answer. I think the bell was ringing, but set it up anyway. Right. So here, I'll recap that one just in case. Right. So number 7 was the elastic collision. What makes it a collision elastic? Well, a couple of perspectives. One is that it's like perfectly bouncy, which is pretty close to what you're looking at right there. And the physics is that not only is momentum conserved, which is just true for every collision, right, but also this special property, kinetic energy is conserved. There's a solution to that system of equations, which is this yellow box right here. I think I may mention too that if you guys take physics in college, if you're doing like some kind of science track, hold on to especially these notes from this week, because if you have to solve this from scratch, then that's a lot of paper and a lot of time. But if you solve it with these notes, it'll save you a lot of time. Right. So for number 7, it's set up. I gave you guys all these numbers. You can kind of plug and chug, and we can talk a little bit more about it, but just in case, plug it in and get the answer. All right, so we're ready for number 8. Now, both number 8 and number 9 are the same concept, something called coefficient of restitution. This is just a fancy physics way of saying how bouncy is a collision. Right? Because at one extreme, you can have perfectly inelastic, 2 objects collide and stick together. In which case, there's no there's no difference in velocity between the 2 objects after the collision if it's perfectly inelastic. It's like your guys' lab yesterday. Okay? The other extreme is it could be boing, perfectly bouncy, all the kinetic energy is conserved. Okay? And how the coefficient of restitution works is, well, it would obviously be 0 for perfectly inelastic, because 0 divided by n is 0. Right? For perfectly elastic, this number comes out to 1, like 1.000. Right? And for any collision in the middle, it'd be, well, maybe like 0.4 or something, somewhere in the middle. Right? Right. So let's see what it is for this one, number 8. Or sorry, number 8. Right. Now, all of us have different numbers, so we're all going to get a little bit different answers, but it's all the same procedure. So let me set up coefficient of restitution is, right, I'm going to set up a ratio. Right. I'll go velocity B post collision minus velocity A post collision. Final to be like post collision, right? Okay. And I want to compare that to what was going on pre collision, like leading into the collision. Now, if I do this way, velocity A minus velocity, or I meant to do that the other way. If I do B initial minus A initial, the weird thing about the way I just wrote this right here is that this will always come out to be a negative value. And there are 3 ways around that. One way around that is to just slap the negative sign in front, which is the same thing as doing absolute value, right? Or what I did on the poster version is actually swapped A and B on the bottom, right? To B minus A, then A minus B, right? So any of those could do it. But I'll use this version here. Let me just go ahead and feed the numbers in. So B final, what have I got on my paper? Right, so post collision. I have this one coming to a dead stop. That's interesting. Meters per second. Okay. Velocity A final says -5. Now I'm subtracting a negative number. Now be careful this week with like subtracting a negative. The same thing as adding a positive. So watch for something like that. Okay. Then before the collision, got the initial. Oh, it looks like oh, this is interesting. Meters per second, right? Every paper I made a little bit different. So I got object B starts at rest and ends at rest, right? And then object A initial as this many meter per second, so that. Right. If you look at pre-collision, post-collision velocities, that could also tell you something about the masses of the objects. Like you could work out at least like what's the ratio of the masses, right? Notice I did not tell you any masses for this question because you don't actually need the masses to solve how bouncy something. It's kind of a material property, right? All right. If I have one of my objects is both starting and ending at rest, doesn't that kind of mean that it has to be sort of infinitely massive compared to the other object, right? I mean, technically speaking, this kind of breaks momentum conservation, right? It could be approximately true. Here, what if one of the objects is like the Earth? What if you're bouncing a ball off the Earth? Well, then before and after the collision, the speed of the Earth basically doesn't change, right? Which could be kind of the scenario, right? Being it that way, right? So isn't it just like 5/8, right? It's negative, but negative negative turns back positive. Okay. So my version is like 0.6 something. All right. Okay. So I could call it like 62%. And coefficient restitution somewhere between 0 and 1. So this is a little bit more bouncy than not. It's kind of halfway in between, a little bit more on the bouncy side. Okay. Make sure I got an answer choice. Bam, right there. All good. Next question, number 9. Also coefficient restitution, but from a little bit different perspective. It says, what if you bounce a ball off a floor? Okay. So coefficient restitution we're taking. Okay. And next week, I'm going to have you guys do a specific version of this, like a modified version, right? Where you bounce a ball off a floor. And depending on the drop height and the rebound height, you can calculate how bouncy it was, right? So remember, coefficient restitution is defined as the ratio of difference in velocities, right? So post compared to pre-collision, right? So it'd be the rebound speed compared to the crash speed. When you guys do this lab next week, maybe you could like hold the speed gauge in just the right place and you could figure out how to pass, but that would be kind of hard to do. It would be a lot easier to do. It's just to break out a meter stick and say, like, well, how high did I drop it from and how high did it rebound to? And you can calculate the crash speed and the rebound speed, which you know how to do from 2 different units in the past in this class. Like last week, you guys remember Galileo drops the ball off the tower. At the top, it's all potential energy. At the bottom, it's all kinetic. And you get this crash speed was like square root 2gh, right? Or you could go way back in the day to kinematic motion. You guys remember the 3 amigos? And you could say, well, based on some drop height, it starts from rest. You can calculate the speed that way, right? However you do it, you always get square root 2gh if it is dropped from rest, or if it goes to like some maximum height, that'd be right, something like that, right? And so I've got 2 different h's. Here's my rebound height, here's my drop height, so I can calculate the rebound speed and the crash speed. Like that, right? Now you divide those two, the 2 and the g goes away, so coefficient restitution looks like this. We do a quick demo of what you do next week for your lab. I'll give you some different balls. I got ping pong ball, rocket ball, and a mystery black ball. I don't know what this is. Right? So, oh, look at that. Ooh, I wonder how bouncy that is. It's bouncy. It's different if I drop it on the, actually it's not very different if I drop it on the paper. It was earlier, I guess. How about the rocket ball? Ooh, how bouncy is that? Okay. How about mystery black ball? Ooh, is that perfectly what? Inelastic? What would the coefficient restitution of be? 0. Ha! Right? Because post collision, there's no difference of velocity between like the surface and mystery black hole. Right. All right. How about the numbers on this page? Let's put it all together. Okay. So coefficient restitution is, see, it's backtrack a little bit. Okay. The square root 2g rebound height over square root 2g drop height. Right. The 2g goes away. Right. So that boils down to more simply coefficient restitution is the square root of rebound height to drop height. What are my numbers? I got 0.80 meters on my paper, so rebound height, and then the drop height was like 1.00 meters. Right? You could also measure in centimeters as long as you're consistent. If it's centimeters and centimeters, you'll get the same outcome. Right? Right. and I'm getting a number, which is this right here. Right? Ooh, that is pretty dang bouncy. I could interpret that as like 89%. I could say that the rebound speed is 89% of the crash speed, right? And that would make it rise to 80% of its original height, right, for that particular bounce. Okay? It's pretty close to the elastic end of the spectrum. Okay, everybody good there? All right, and last couple questions, 10 and 11. These are both, well, it's like the same scenario. These are both impulse questions, right? You hit a baseball bat with a baseball is the premise of both of these, right? So I just give you different variables for it, right? But like a lot of the here, you guys have probably figured out. I mean, you could just take the equations on the front or on the posters and kind of plug and chug and get the answers, right? But there's some more details I want to fill in too. Right? So I told you the mass of the ball, and then I told you for this one, see the force from the bat and the time interval of the force act square, which is a tiny, tiny time interval, right? Which makes sense. Yeah, I'm talking about collision, bat on the ball, some tiny fraction of a second. Right? And the question is, what's the change in velocity of the baseball? So let's answer that, and then got some extension questions, but one thing at a time, right? I'm thinking of this poster right here. Right? Oh, hey, look at that. That's the picture that exactly aligns with the story that we're doing. Right? So bat hits the ball. Right? And if you look on a force versus time graph, okay, it would look like this. Right? Realistically, what happens is most of these type graphs, you open up any standard physics textbook, they're usually triangle-shaped type graphs. And why would that be? Because the ball makes contact with the bat here, then pushes harder, right? Then right about here, the ball finally starts to reverse direction, and then finally breaks contact with the bat right here, right? So in slow motion, it'd be like this whole process, right? The area under that curve, the area of that triangle, represents the impulse. That's the transfer of momentum, right? And you can kind of simplify it with this equation type to say, well, average force times time, which is kind of like the area of that rectangle, which is the same area. But notice that the height of that rectangle only tells you the average force, which is kind of what feeds into this equation here. Okay, so more on that later. We're going to come back to that idea. You know what else too? This is a force versus time set of axes. Last week, you guys saw a similar concept of force versus distance. If you push on with some force for some distance, that's you're transferring some amount of energy to some object, right? And the physics term for that was called work, right? This is force versus time. We're transferring some momentum, and the term for that is called impulse. Okay, so just to compare a couple of ideas there. Okay. So let's do, this is number 10. Right, you guys saw the picture, bat hits ball. Mass times change in velocity results from some force for some time interval. Okay. Now that's an average force, right? And we're trying to figure out what's the change in velocity given everything else, right? I'm gonna kind of solve in terms of variables here because I can do that at one step. Just divide down the mass of the ball. Okay. So the change in velocity of the ball is what is the average force for some time interval, right? If that was the graph, you just find the area of the triangle would be that numerator and divide by the mass of the ball. And pop in some numbers here. I've got a force of this many newtons on my paper for this tiny fraction of a second, acting on a mass. Here's a baseball right here, this many kilograms. Boom, boom, pop it on. Okay. More force, more changes velocity. More time it acts for, the more change velocity. The larger the mass of the ball, the less it changes what it's doing. Makes sense too, inverse relationship. So that force times that time interval on that mass, I'm getting this many meters per second. I should have asked you guys what the unit would be, but you guys would have said, oh, talking about velocity, it's got to be meters per second. So that's an answer choice. Yep, boom, right there. All good. All right, so you guys get it? All right, so extension idea on this. I wonder what the final velocity of the ball is, because that wasn't the question. The question was what's the change of velocity. Okay? So think about this. If the ball was sitting on a tee, it's supposed to just sitting there on a tee starting from rest, right? And then you whack it with this force for this time, that ball, blah, 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 right? Well, in that case, that would also represent the final velocity of the ball, because it would go from 0 to change this much. So that would be the final velocity leaving the tee. If it's just sitting on a tee, you whack it. But what if a pitcher throws the ball and it's in motion and the batter swats it back the other way. So let me draw that scenario, which is a different type background. Right? So here's a ball. I'm just going to make up a number, for example. Let's suppose, for example, the pitcher throws the ball at 10 meters per second, right, which is about 20, 30 miles an hour, so not that fast. Right? 10 meters per second towards the plate. And the batter, bam, hits it and it rebounds back the other way. Right? Who could tell me? See if you guys can put this all together. Extension question right here. How fast did this ball rebound from that bat? Who can figure that out? It's a little bit tricky question. 12 meters per second, right? Right? Because here, look at this. The change in velocity, isn't that final velocity minus initial velocity is the change in velocity, right? I'll work backwards from the answer here, right? So if it left the bat at 12 meters per second, it was thrown at 10 meters per second, but don't forget the reversal in direction, right? Velocity is a vector value, just like momentum or impulse are also vector values, and force is a vector value. Direction matters. Left to right, I need to include a negative sign. Maybe I'll stop a negative on this guy just to easy, meeny, miny, mo, pick one. Right? So I need to subtract a negative value, right? Subtract a negative. It's like adding a positive. Okay. There's your 22 meter per second change of velocity, which matches that right there. Right, guys, that? Right. If the pitcher pitched the ball at its different speed and all these numbers played out, you maybe get something different, right? I just made up the pitching speed number, but it would work out like that, right? Right. And last question. So same scenario, bat hits ball, but this time, okay, I gave you the mass of the ball and the time interval, right? I also told you the change in velocity. So maybe we brought a speed gun to this game and we're getting the pitching speed and the rebound speed, and we do this whole thing like taking the difference in negative values, blah, 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 right? Okay. And I did all that work for you and give you a number, change of velocity. Okay? And the question is, what force from the bat set that in motion? So that's what we're going to answer right here. Right. I should say what average force, because I got an extension question on this one too. So one thing at a time. Right. Average force for some time interval results in some mass times change in velocity. Right. If you like, that is what impulse is. So impulse has these two perspectives. Change in momentum is caused by some average force for some time interval. Okay. I gave you 3 of those numbers, so we're solving for average force. Let me go ahead and do the algebra first before I plug in anything. Okay. So it's mass times change in velocity, all in some time interval. That's what that would be, right? Just like that. Right. And one reason I want to solve this in terms of variables before I plug in any numbers in is to have you guys see here. Guys, what is change of velocity per change of time? If I just look at that part right there, guys, what is delta V over delta T? What's that called in physics? Rate change of velocity. There's a name for that. Acceleration. That's the acceleration of the ball while it's being hit, right? Oh, F equals ma. Hey, is that Newton's second law of motion right there? Newton's second law of motion, right? There is a these guys are next door neighbors. Newton's second law of motion and the impulse equation, they're like next door neighbors, right? Some physics teachers even say they're kind of the same thing. So let's plug in some numbers at this point. I got my baseball, has this mass, got many kilograms. I went ahead and told you the full change of velocity, so let's just plug that in. And then time interval, this many seconds. Boom, boom, boom. So that ball changes that velocity in that time. Right? Looks like this would have been the average force in newtons, that many newtons for average force. Okay. Make sure that's an answer choice. Yeah, that's an answer choice. Boom. Right there's these. All right. Working out for you guys too? Good. All right. So here's my eccentric question on this one. Suppose you go to the store and you buy a baseball, but you can't buy the nice one because maybe, oh, I'm super poor, but hey, I can buy one of the cheap ones. And it says on the package, this baseball is good as long as you don't hit it with more than, 500 newtons of force. As long as you keep the force under 500 newtons, then you'll have a fun day, right? But you whack this ball with like more than 500 newtons of force, and all the seams are gonna bust apart, and well, then you're done playing. Right? So is this baseball safe? Right? I whacked it with all these numbers. Right? Here's my average force. Remember, the baseball can withstand up to about 500 newtons. Beyond that, the seams are gonna break apart. Right? Is this baseball safe? Let me see. Show of hands. What you guys think? I guys think, yeah, that baseball probably safe because that average force is less than 500 newtons. How many guys think, no, I think this baseball is going to be all busted up? You think this baseball gets all busted up? Yeah, you're right. And how'd you know? How'd you know that baseball gets all busted up? Exactly. The maximum force is more than the average force, right? In fact, if it's exactly a triangle shape, it should be times 2, right? I bet the actual like maximum force in this ball is upwards of like over 600 newtons. You guys think? Right? Because here's 315 newtons. Here's like 630 newtons. Right. I bet that baseball gets busted up like right about here. Right, you guys think? I think so. Ooh, fun extra things to think about. Okay, so that's all the questions on this half page. If you guys turn this into the grade trade before you leave class today, then I can put that in the grade book over the weekend. If you need a few more days on that, then you can turn it next week too. That's okay. But we're going to switch over and solve as many of these chapter 9 puzzles as we can before the weekend. Get close to the weekend here. All right, first question, number 55. Bullets. 2 bullets, equal mass, shot at equal speeds. All right, already I'm thinking that's same momentum, right? Also same kinetic energy for that matter, but they went that direction. Right? At blocks of wood on smooth ice rink. Okay, that's a physics word for negligible friction. One bullet made of rubber, boing, bounces off the wood. The other bullet made of aluminum burrows into the wood. Which case does the block of wood move faster? Ooh. Hey, this sounds a lot like your starter question yesterday. It's like nearly identical. So I'm gonna draw this one out. Think about this. Okay. So we got two bullets. Okay. We got a rubber bullet with some mass moving at some velocity, and we got a aluminum bullet with identical mass moving at identical velocity. Right, so got the same momentum. Okay. They got to run to these blocks of wood that are sitting on ice rink. Right, it's like identical blocks. I think I remember the whole thing. Right. Okay. The rubber bullet is gonna boing, right, bounce off, like rebound, and the aluminum bullet's gonna stick in the block. Okay? And then both of these are gonna slide on the ice, but they're gonna slide differently. One goes faster than the other. Okay? If you remember the starter question from yesterday, then you probably already know the answer. So let me see, show of hands, what do you guys think? Who's going to move, like slide off faster? Like scenario A with the boing rubber bullet, or scenario B with the aluminum bullet? Who slides off faster? Show of hands. How many guys think rubber bullet block is going to slide off faster? Yeah, you guys are right. Because it's going to transfer more momentum was the explanation from yesterday, right? So, like here, maybe the aluminum bullet's easier to analyze because mass times velocity. The momentum it collectively slides off with is mv, right? Okay. Like if it's here, I'll make up some numbers. Let's call this guy 1 kilogram, which is again like more like a cannonball from yesterday. Right? Maybe we've got some cannonballs going on. Right? This guy 1 kg, right? Moving at let's say 100 meter per second. 100 meter per second. Right. Well, this whole thing is going to slide off with a momentum of 100 units, right? 100 kilogram meter per second. Just pick up some numbers. Okay. If the rubber bullet, the boing bounces off with like 70 meter per second rebound speed, right? Then what's the momentum for this block of wood right here? Guys, what is 100 minus negative 70? Yeah, positive 170, right? Because that's 100 plus 70. Minus a negative, that's like plus, right? Then times 1 kilogram mass, just make the numbers easy, right? That's like 170 kilogram meter per second. Yeah. In fact, if you go up to like twice as fast at the end of the day, right? Up to that much. Right. Number 61, volleyball. A 0.24 kilogram volleyball. I'm going to do a quick Google on this because the AP textbook had a slightly different mass on that volleyball. What is the mass of volleyball kg? I want to know. okay, they gave a range of values, say somewhere between 0.26 and 0.28 kilogram. Okay, well, I guess you guys have a small ball. Small ball approaches Tina with a velocity 3.8 meter per second. Tina bumps the ball, giving it a speed of 2.4 meter per second in the opposite direction. Kind of makes sense, right? Right. Now, if you turn your brain off and you're just looking at the numbers, you might forget that there's a negative number somewhere involved, right? Because notice they said speed, not velocity, right? It changes direction. Velocity is a vector value. Momentum is a vector value. Force is a vector value, right? Somewhere I need to throw a negative number in here. Right? What average force did she apply? Blah, blah, blah. Oh, they gave you a time interval. Ooh, that would be good to know too, right? Got to know the time interval to be able to solve this. Right, so 61. Okay, let's draw this out. All right, so let's give Tina some hands here. Just gonna. Then here comes a volleyball. It's gonna boing. Right, it's gonna rebound. Okay. Oh, what they? Okay, so they told you the mass of the volleyball was this many kilograms. Right, you Googled that. Looks like it's on the small side. Let's go with it. It said it's coming in at, I'll call it V naught is 3.8 meter per second, and then the rebound speed they said was 2.4 meter per second. Right now, if I turn these into velocities, then I have to have a negative somewhere. Okay, I'm gonna call them left negative and right positive. So I'll actually make this negative 3.8 meter per second. I should have saved space for negative. How about this? Okay. Equals negative. How about that? Okay. And one more thing is they said this collision. Whoops, meant to be have it hitting your wrist. That's more what you do with the volleyball. But oops. Right. Anyway, let's have the time interval of that collision. Bam. Be said 0.025 seconds, right? Tiny time interval for these impulse questions, right? Oftentimes, right? What's the force? Right, so let's do well, average force, I know could be mass times change in velocity, all divided by time interval, right? That's kind of the Newton's second law of motion version of the impulse equation, right? Okay. Let's look at impulse on the poster. Impulse on the poster looks like this, right? Mass times change in velocity, force times time interval equal. Right? Take the time interval, divide that over here. Looks just like that. It's a lot like Newton's second law of motion. F equals ma. If you like average force, okay. Here I'll just go ahead and start plugging stuff in. Right. So we got this many kilogram, that many kilogram ball. Time. Okay. Now change of velocity. That's final minus initial velocity, right? Okay. Now final velocity, I got 2.4 meters per second. Okay. Minus initial velocity. Here's where I'm subtracting a negative. Subtracting a negative. So be careful about that. Okay. And then this all happened in this many seconds. Okay. All right, let's do that mass ball times 2.4 minus the negative becomes plus plus. And then it's all divided by that time. That many Newton. Oh, I should have asked you guys what the unit was going to be. You guys would have said Newtons because we're talking about a force. Right? Kilogram meter per second, kilogram meter per second squared. Oh yeah, it's definitely Newtons. Right? That's about 60 Newton force right there. Very good. Number 66. Oh, a 0.15 kilogram ball, which is, by the way, is approximately a baseball, moves in a positive direction at so many meters per second, is acted on by a force shown in the graph. Oh, force versus time. Force versus time graph. If you ever open up a physics textbook, you see force versus time, almost for sure the question is going to do something with impulse, something with momentum transferred, right, which of course is the theme of this chapter, so of course it would be, right? Okay. What's the ball speed at the 4-second mark, which is like after the force has been applied? It's like a variable force, right? Right. So 6K6. I can say mass times change of velocity. I solved this a little bit different ways earlier today, but mass times change of velocity comes from, well, I could say average force times time. I'm going to write this a little bit differently here. Some of you guys might be in calculus. I'm going to use some calculus notation here. I'm going to say, break out a, how many guys know this? What is this right here? What did I just draw? Integral. Right. All an integral means, some of you guys know this, right? It's just the area between the curve and the, in this case, the time axis, right? It's like the area of the triangle if it's a triangle shaped graph, right? And oftentimes for impulse graphs, you get force first time, you get triangle shaped graphs, right? So I'll do force as a function of time times dt, right? In case you're not in calculus, I'll tell you guys what this means. So force as a function of time is like the function, which is the case could describe the triangle shape, right? And then dt, what that kind of means is like, if you guys learn integrals one day in calculus, take calculus, right? Some of you guys have, right? Then if, usually how you taught this is like if you divvy this into like a bajillion, like infinitesimally skinny rectangles, you know, like add up all those little tiny rectangles, right? Basically gives you the whole shape of that triangle in the case. So dt is like a tiny sliver of time. Okay, so that's just notation for that. But for you guys, all you care about is that's the area of the triangle because it is a triangle shaped graph, right? Which for us is like 1/2 base height, right? 1/2 base height, right? So that's all we're gonna do, right? Yeah, let's do it, right? So right. Mass of the ball was 0.15 kilogram. What's that? Times change in velocity. Could that be? Right, I'll just leave that as delta v right now. Delta v. Solving for. Right? There's one more thing we got to do to answer the question, but we'll come back to it later. Right? Is the impulse delivered is 1/2 base height on a force versus time graph. So 1/2. The base of the graph is, okay, well, it goes from 1 second to 3 seconds. So that's a good 2-second time interval right there. Right? We'll call that 2 seconds. And then the height of the graph goes up to 2 newtons of force. So 2 newtons of force. Right? Is that okay? All right. So there's the impulse. Looks like 2 Newton seconds of impulse. Divide by 0.15 kilograms. Here, delta V is, so this all comes out to 2 Newton seconds of impulse. I'm going to divide by the 0.15 kilogram mass that that impulse acts on, right? So 2.5. Okay. So I'm getting a change of velocity of 13.3. Oh, guys, what would the unit be? 13 what? Meters per second, right? Newton seconds, an alternate unit for that is kilogram meter per second. Cancels out with this kilogram, leaves you with meters per second, which describes something to do with the velocity, change of velocity. Right? Actually, that doesn't quite answer the question, but that's an important middle step right there, right? Okay. That's the change of velocity. Now, on the half page, I brought up this idea of like, well, what if the pitcher like throws the ball and you have change of velocity? What's the like post-collision velocity of the ball? That's kind of what we're getting at right here. They told you an initial velocity, right? And then something to do with like a impulse delivered, right? So what's the final velocity? Okay. Now here's where maybe it kind of depends how you interpret this question. Right? So I'm going to split this paper in half and give you guys 2 different answers, right? Depending on your interpretation. Okay. So I think the way that they're intending it to go is like they give you all positive numbers. Like the velocity was positive, the force is positive. I think they're saying like this ball is in motion. Right, here's the ball, it's in motion, and then you, bam, bump it and like speed it up. Right, I think it's what they want to say. So if force is in same direction as speed, right? But what might be a bit more realistic is like the volleyball or the baseball questions where like it's headed one way and bam, you hit it back the other way. So I'm curious to see how the numbers would play out in that case. So if force is opposite of v naught, right, of the initial velocity, right, something like that, right? So we'll try either way. Right. Here, how can I say this here? Okay. So there's different ways you can apply this to. Maybe I'll just go from the delta V situation. Okay? So I know that delta V is V final minus V initial. That would be true for either interpretation. Right, we're supposed to solve for V final here. Right. So my delta V was 13.3 meter per second. It's also 13.3 meter per second. V final, we're solving for. V final, we're solving for. Okay. Now here's where okay, what was the initial direction of the ball? Okay. So if it was in the same direction, then I'm subtracting off like same direction. Right? They gave you a number. What was it? They said 12 meters per second. So I do minus 12 meters per second. Right. But if you are actually batting it the opposite direction, then I do minus negative the initial velocity. Like that. Right? Which, just like you guys seen a few times today now, minus negative is plus positive. Right? So this and right. So here, just add that over, getting V final. You could also go through impulse and divide by the mass of the ball at the end. You could do that too. There's a little bit different ways to place out. Right? So this comes out to like I think 25 some meter per second. Right. I think if you guys like find the solution online or something, I bet that's the interpretation they went with. Right. But if you interpret it the other way, see how that would play out. That's like I think this number, that many meters per second. Felt a little bit differently. Okay. Right. So if the ball's moving along and you bam knock it even faster, then it looks like that. Right. If it's going one way, you bam knock it the other way. Ooh, that's more like a bunt, maybe like point, like lay down a bunt kind of deal. Yeah. All right, guys got that? All right, number 67, baseball. A 0.145 kilogram baseball. Yep, it's about a baseball. It's moving at so many meters per second. When it's caught by a player, find the change in momentum of the ball. All right, there's a couple of follow-up questions. If the player catches the ball, holds his mitt stationary so that the time of that collision is, bam, really tiny, what's the average force? Versus question C, what if you move your mitt backwards while you're catching it, therefore extending the time interval of catching it? What happens to the average force? All right, so 3 questions. Let's do one at a time here. Question A, what's the change in momentum of the baseball? Now, the change in momentum has nothing to do with how you catch it. If you catch it with an abrupt stop or if you move your mitt backwards, either way, the impulse is the same. So 67. Maybe I'll draw this out first. All right, draw this out. Right. Have a mitt. Right. Pocket the mitt. Here comes the baseball with some initial velocity. Right. It's on the move. Right. It's got some mass. Oh, they give you those numbers. So I'm going to write those numbers in. Here's the mass of the baseball, that many kilograms. Okay. The initial velocity they gave as this many meter per second. If you like, you do know that there's going to be a force from the glove that acts to the right to slow it down. So maybe if I want you, I could call this negative just to make the force positive. I don't know, maybe something like that. Maybe that. Right. So what's the impulse on the ball? Change in momentum of the ball. Change in momentum of the ball is mass times change in velocity of the ball, right? Which is mass times V final minus V initial, which is 0.145 kilogram times, okay, V final is going to be 0 meters per second because it's brought to rest. And V initial was the starting speed. Like that. Put it all together. What is that times that? Last time change of velocity. I'm getting, is that right? Okay. 5.05. That could be kilogram meter per second. Or alternatively, you could call that this many Newton seconds. Right. Those are identical units. Kilogram meter per second and Newton second are identical units. Oftentimes, if it's an impulse, like a transfer momentum, you'll see like Newton seconds. So see about this. Change momentum. There you go. Okay. All right, good so far? So that was question A. Okay, that's regardless of how you catch it. If you bring it to an abrupt stop or if you move your back, go back, right? Either way, question A works out the same. Right? Now, question B gets more into the details of how you catch it. B and C, we're really gonna compare those two. Okay. So B, they give you a time interval of like 0.05 seconds. So abrupt stops, bam, all of a sudden. They say, what's the force? Let's jump straight to the force version of the impulse, right? So we've got an average force, right? Is change in momentum per time interval. That's what we're doing, right? Mass times change in velocity over time interval. Let's look at impulse formula again, right? So it's this place right here. The question is, what's the force? So that's the impulse divided by the time. Just exactly right there. Put some stuff in. Right? You know from part A what the impulse is. It's this many. I'll call it Newton seconds. How about that? Okay. And this all happens in 0.050 seconds. Second this way, right? Oh, which would give us newtons, which describes force. So that. I'm looking at this many newtons of force. That many newtons of force. Right? Is that? Question C. We're just going to change one thing. We're going to extend the time interval of that collision because we're moving our mitt back while we're catching it. Right? Oh, guys, what do you think is going to happen to the force on the ball if you move your glove back? Imagine that. Imagine you catch the ball, bam, abrupt stop like that, versus if you move your glove back while you're catching it. Is it going to sting as much? Yeah, it should be a smaller force, right? So if we extend it like 10 times the time, that's 10 times the time, isn't it? Right? Ooh, do you think we're going to get a tenth of the force? Huh. So F average. I'm running out of paper, so I'll just go ahead and plug the numbers in. It'd be the same impulse, same mass of the ball, same initial velocity, same final velocity. So none of that changes. But I am going to extend the time interval by a factor of 10. So, oh, look, there's, it's 1/10 of the original force. Yeah, 10 times the time is 1/10 of the force. That's the relationship. It's an inverse relationship. Makes sense, right? We're good there? Let's come up earlier today. I'm gonna flip my screen and show you guys a related concept here. Let me find where I can flip my screen on Zoom. Here we go. Okay. Have you guys ever noticed one of those driving down the highway? Yeah, right. If you haven't, next time you're on I-95, take a look outside, right? So suppose you're driving your car, it's all kind of good, right? But maybe, who knows, spend a lot of hours on the road. You guys know 40,000 people in the United States die every year in car crashes, right? That's been true for a long time. I mean, you get distracted, you get tired, stuff happens, and you make one little mistake and boom, oh, look at that concrete barrier right there. You want to make a mistake and crash into that? Ooh, that'd be a bad day, maybe your last day. But if you throw this attenuator right here, this is for safety, right? This is for safety, right? Guys, if you crash into this, it extends the time of that collision. Now, notice what's not changing. The mass of you and your car is not changing. The change of velocity is also not changing. Maybe going from 70 miles an hour to 0. That is right. Right. The impulse doesn't change, but the time is extended. Therefore, the force of that crash is decreased, right? Or you could put it in kinematic terms too. Say the acceleration also decreases, blah, blah, right? A little bit different ways to think of that. Right. So back over here. Right. Okay. So similar idea of catching a ball. Right. Number 70. I think this will be the last one we'll do today. Number 70. Rockets. Small rockets used to make adjustments in satellites. We got a thrust force on this rocket. We need to take the spacecraft, which is 72,000 kilograms, take like 50 cars parked, right? So big old satellite. We need to change it by 63 centimeters per second. How much time should the rockets be fired for? So they come to you, you're the engineer, you're like, oh, well, this is an impulse question. I think we got just enough time, right? Force, well, it would be a constant force, wouldn't it? For some time interval, that's the question. It's going to result in the mass of this satellite. Yeah, right. Changing some velocity. Okay. So the time interval is just going to be the mass of the satellite times however much we change velocity divided by the thrust force. So let's plug some numbers in. We got a 72,000 kilogram satellite, right, big old satellite, Like about 50 cars. Right? We need to change back. Ooh, 63 centimeters per second. Guys, is that 63 over 1,000 meters per second? You convert to base SI units. Okay. And the thrust force that's going to put this all into play is 35 Newton. Right. Which, by the way, is about 3.5 of these worth of like force, right? Like if I pick this up, this is 10 Newtons of weight. Okay, so like 3.5 of these worth. All right, so we go. So it's maybe like 50 cars worth of mass. And so put it all together here. That times that over that. Okay. Hold on. 60, 35. Did I do that right? 63. 73 centimeters per second. Oh, whoops. Guys, I made a little mistake. Centimeters per second. Oops. Is that that's divided by 100, right? Oops. Yeah, we'll keep one of these zeros. Keep one of these. That's right. Get rid of these guys. How about that? Right. Times 10. Some look weird. All right. So that's this many seconds. If you like, let's do that's 21.6 minutes. Minus 21 minus 60. Right. Or 21 minutes and 36 seconds. All right, there you go. Here's our PowerPoint on this week. If you turn in that momentum half page, then I'll get that in the grade book. Right, and hope you guys have a good Veterans Day 3-day weekend, and look for a rocket launch around 8:28 tonight. Oh yeah.